from you.
Thank you, Maria. Thank you for that very nice introduction. Let me bring up my slides here.
Okay, it's good. I think maybe you want to make it into a slideshow.
Yeah. Slideshow. Where is the slideshow? Yes, here we go. All right, how is that? Can everybody see everything there?
Perfect.
All right, well, I work at the Lawrence Berkeley National Laboratory. And for those of you who are not familiar with the National Laboratory System, the laboratories are U.S. Department of Energy facilities, which means that the computer that I'm talking to you on is actually owned by the Department of Energy. But I am not a civil servant. I'm an employee of the University of California. The University of California manages the Lawrence Berkeley Laboratory under a long-term management contract for the Department of Energy. The lab provided me with this lovely background. I don't know if you can see it. It's a view of the laboratory with snowflakes superimposed over it. It rarely snows in Berkeley. I think in the 4 years I've been in Berkeley, it's maybe snowed 3 times. But I thought for the festiveness of the holiday, I would adopt that screensaver. So I'm going to talk about reliability and resilience. I'll talk. In fact, let me talk about. Maria, you asked me to talk about what we do at the lab. This is a sample of the kind of research that I've been most directly involved in. Some of you know me from the work I do in certs with the technology side. This is more, I would say, on the analysis side. We have a lot of work that we do on reliability and resilience metrics. And one of the things I'm very happy that we were able to work with the Department of Energy on was to get EIA to begin mandatory reporting of reliability by utilities following the IEEE standard 1366, which prescribes ways of defining safety in a consistent manner. So that has gotten me to be involved with the Distribution Reliability Working Group at IEEE. And we've done a lot of work analyzing. They have a method for segmenting major event days, and we did an analysis to try to demonstrate what biases may or may not exist in that method. I'm also a member of the NERC Performance Analysis Subcommittee, which prepares the annual State of Reliability Report. And I've been working, one of the things I've been most focused on, and I haven't succeeded yet, is trying to get consistent information reported on the reliability of the bulk power system, which of course is now regulated by FERC, as compared to local distribution systems, which are regulated by either state or local authorities. And my feeling right now is, the ultimate measure of reliability is whether the lights are on. And until we have those measures separately distinguished between the 2 jurisdictions and how electricity is managed in this country, we won't really have a complete picture of how well each is performing with respect to its basic mission of keeping the lights on. Now, today I'm going to deviate a little bit. I will talk a little bit about metrics, but I want to talk more about sort of what the value of reliability is. And because resilience is such a big topic these days, I'm going to spend a few minutes giving kind of my personal views about the differences and relationships between reliability and resilience. I think there's a lot of discussion, and I just sort of like to get my version of it out on the table early. Then what I want to do is introduce a very old discipline called value-based reliability planning, which is a means for taking into account the costs that unreliability imposes on customers into decision-making around how much reliability to invest in. So it's a way of thinking about how to rationalize how much we invest in reliability. Then I'll spend the rest of the talk talking about methods to estimate or provide information about what power interruptions cost customers, the input to this kind of basic benefit cost framework that I'll be outlining for you. And I'll conclude with some of the current research that we're doing at the lab to try to advance some of these methods. And as I indicated before many of you came on, I'm much more comfortable having a conversation in these kinds of talks. But I'm also very bad about being able to see the chat box or look at people raise their hands. So please do raise your hand or put things in the chat, and Dan and Maria assure me that they'll be sort of scanning that, and they will interrupt me at whatever point makes sense to try to answer your questions. Because again, the purpose of this is not for you all to hear me talk, but for me to provide the information that you're interested in. And I only know that if you ask me questions about stuff that is of interest to you. All right. So let's talk about reliability versus resilience.
Excuse me, Joe.
And
yeah. So just before we lose you, I know that not everybody knows standard 1366. Can you?
Surely. So IEEE standard 1366 is a guideline that is promulgated by the Distribution Reliability Working Group, which is part of the T&D committee in the Power and Engineering Society at IEEE. And it defines the basic terms of distribution reliability. And so many of you have heard of terms such as SAIDI, System Average Interruption Duration Index, or SAFE, System Average Interruption Frequency Index. Those are all terms that are defined in the 1366 guideline. A couple that you might, and of course, one divided by the other gives you CAIDI, Customer Average Interruption Duration Index. But a couple that you might not be familiar with that I may refer to a little bit, particularly in the context of resilience, are one's called CLID, Customers Experiencing Long Interruption Durations. And those are measured in hours. And so you can begin to bin customers who've experienced interruptions of 8 hours or longer, or 12 hours or longer, or worse. Another one that is of increasing interest is called CME, Customers Experiencing Multiple Interruptions. And that's also indexed by the number of times customers might be interrupted over the course of the year. These are very important adjuncts to SAIDI and SAFE, because SAIDI and SAFE are really highly aggregated values. They really don't speak to the interruption in experience of any particular customer. It's really the sum of all the interruptions that might take place without reference to who specifically was experiencing them. And so these additional metrics like CLID and like SEMI help get at folks who might be particularly disadvantaged by the reliability experience that the utility is providing to them. And we can go more into that. I'm probably not going to talk too much about those.
Just one more clarification. I'm really sorry about interrupting, but just to put things in context, then NERC doesn't do these standards because NERC only worries for bulk power system, right? NERC.
Well, there are some voluntary reportings around event analysis that speak to loss of load due to interruptions caused by the transmission system that's operated by the portion of the system that is regulated by NERC and ultimately FERC. But it's done not done consistently. And so the way we've tried to get at it is that in the EIA reporting forms, we request that utilities provide us what portion of their SAIDI and SAFE is due to what's called loss of supply, things that happen upstream of the distribution system. And then we ask utilities to report on what voltage they view the dividing line between their distribution system and the transmission system. And so, when the dividing line is 69 kV or higher, that's mostly the bulk power system. But many folks take service at sub-transmission voltages, and so it's much harder to tell. And we've actually written a paper both with members of the Distribution Reliability Working Group and also with NERC, reporting on that information. And at least to a first degree, based on the data we have, we can show that the transmission system that's regulated by NERC, is highly reliable compared to the distribution system.
Yep.
Less than 5% of the interruption duration that people experience in a given year is due to problems that originate on the high voltage transmission system. The vast majority of power interruptions that customers experience are due to problems that happen from within distribution. And so, trying to keep those, and of course we have mandatory reliability rules that enforce that reliability behavior by the transmission operators. And one conclusion is this stuff pays off. The other conclusion is that that distribution is a very, very vulnerable part of the electric power delivery system, and it's really the source of most of the interruptions that customers experience. And therefore, if you're trying to get very serious about reducing or improving reliability, you can't overlook distribution as a place to start. And we'll come to that in some of the discussions that I'll have for today. Anything else, Maria?
Thank you. I muted myself. Sorry. Thank you.
All right. Well, I wanted to talk at first about something that's on a lot of people's mind, which is reliability versus resilience. And I want to both contrast what's common and what's different. And I've broken it up into a couple of dimensions. And this one slide talks about features, metrics, and actions. And the features of reliability that define it are that they're routine events. They're not planned, but most people have experienced a short duration interruption in their electric service. Big events, like after a big storm, often make it into the local news. Resilience events, on the continuum of power interruptions, really are just at one end of the continuum. They're infrequent, they're all generally unplanned, but they're big, they're widespread, and they may last long periods of time. And because they are widespread, and because they may be long in duration, they often have significant corollary impacts. And the simple rule of thumb, is the I know it when I see it. My I know it when I see it is when it's in the front page of the New York Times. That's a resilience event. If it's just making it into my local news, I'd call that a local event. And so this issue about how many people know about it, how big the impact is, that's really the distinction. But in terms of power interruptions, it's really completely capturable within the existing metrics of SAIDI and safety. In fact, I talked earlier, there are provisions in SAIDI and safety for major events, which segment the very largest events from the routine, everyday types of events. But in terms of the metrics, the one certainly 1366 as an example, it's all focused on the continuity of electric service. And it really does not speak to some of the other impacts that are associated with what happens when electricity is not available to customers. Similarly, you can do these same kinds of counts on an event basis with resilience. And I think this is another very important distinction for resilience versus reliability. Resilience really, I think, needs to be framed in terms of the specific event, generally a particular incident in which a large amount of power is lost. And so there's a specific cause that can be associated with it. And so when you talk about resilience planning, it's often about identifying what is the cause and what are you going to do to try to be more resistant to that cause of unreliability, and what you're going to do to try to recover from that cause when it occurs. And the examples that most people are familiar with are things like hurricanes or wildfires or earthquakes. And so again, it's an event-specific kind of phenomena, and that's why a lot of the metrics that you might use, they're very tailored around the type of event that took place. So, like number of customers affected, hours that they are without power, how long it took to restore service, and because, as I've mentioned, they're such they have such significant corollary events. There's a lot of emphasis on what were those costs, what were those associated impacts on human health being among the most notable, but of course, business interruption and damage. And so a lot of the economic dimensions come into that. Now, in terms of what to do about it, I think the steps are essentially the same. The scale is just very different. You plan to do your best for what you expect. You manage and seek to endure while the event is taking place. You try to recover as quickly as you can. And then afterwards, you look at and review what you did and see how you might do better the next time. Those are the same steps whether you're doing reliability planning or whether you're doing resilience planning. But because of the characteristics of resilience that I'll describe on the next slide, there's a lot more complication. So let's talk about some of those complicating factors. I think the first complication has to do with the entities that are involved in decision-making around these two things. Reliability is sort of a standard practice of distribution planning. There's a well-structured set of fora, namely the rate case or interaction with the state PUC. The regulator is looking at what the utility proposes to spend to improve reliability. There are interveners that say, they're spending too much or they're not spending enough. And it's a very sort of established protocol for how that discussion takes place, with ultimately rates being raised or specific requirements being placed upon the utility by its regulator. So in the case of resilience, though, because these events are so much larger, you have the existing forums, but there's a lot more parties involved. And with resilience, I've seen this many, many times, and where, because of the severity of the impacts, yes, the PUC and the utility are the forum, but many times they're operating under a very specific order from the governor saying, we will not let this happen again. We want you to convene a special set of hearings about this hurricane and what you're going to do about it to make, make sure our population is not as affected the next time this thing comes through. And so you see this time and time again. It happened after Sandy. It happened after the ice storms in Michigan. It happens after the wildfires in California. But this takes on a political dimension because bodies above and beyond the PUC and its utility are really kind of looking over the shoulder, directing some of these actions. In addition, because many infrastructures are affected by these resilience events, many more parties also have resilience responsibilities that need to be coordinated with those of the utility. I'm thinking specifically about local communities. And so they have their own proceedings about how they want to improve community resilience or how they want to address public health needs. And so those who are operating in parallel, they often have standing in what the utility is trying to do. A lot more people at the table, a lot more opportunities for a lot more factors to take into consideration in the utility planning venue. So as if having more people at the table wasn't enough to make these things more complicated, what really makes resilience much more complicated than reliability is the fact that these things don't happen. Thank goodness they don't happen very often. With reliability, we have actuarial records on how often squirrels get electrocuted and how often the wind blows the trees into the lines. And, you really can, do, reliability-centric maintenance planning because you have these actuarial types of records to look at what your exposure is. And, it's sort of understood that you need to spend money to keep the distribution system together because of these routine threats that it's going to be faced with. And so it's kind of a matter of, the cost of doing business. With resilience, because these things don't happen very often, you really don't have a strong empirical basis to apply some of these, probability or based planning kinds of techniques. And in fact, you have very, very different perceptions of what the risks that are involved and what society, what the utility should be doing about them. You have to have shared responsibilities, I indicated earlier, about who's responsible for taking some of these actions. And, of course, you can't really test some of these things because, these things don't happen very often. And then, I think what's, fundamental here is because of these intangibles, the not knowing how often it's going to happen or how bad it's going to be, the need for lots of parties to be involved besides the utility, there's really an essential role for political leadership to sort of cut the Gordian knot and say, we are going to spend this money or we are not going to spend this money. And, I used to think of politics as kind of a dirty word, but, this is what politics is designed to resolve, which is these very complicated issues and where the interests of many, many parties need to be weighed and a decision needs to be made about how we're going to move forward as society. So that's my kind of quick and breezy summary of the relationship and differences between reliability and resilience. I'm going to probably skip over the next slide, which comes from work that we did with the DOE Grid Modernization Lab Consortium. There's no end of metrics that you can use for resilience. It all boils down to what decision are you trying to make? And it turns back to this fundamental insight about what are metrics for? Metrics are for managing things. So depending on who is managing what, that will define the metrics that are relevant for the management tasks that they're going to be judged by, or that they need to judge their actions by. And so people even say we need a resilience metric. I think we need to talk about what resilience decisions we want to make. And I think the metrics fall out as a natural consequence of understanding what those decisions look like. So that's kind of the end of my discussion about reliability and resilience. I'm going to turn now to reliability value-based planning. Before I leave these slides, I haven't looked at the chat or so if folks have a question, but this will be the time to ask those questions. All right, I'm not hearing any. Let's talk about reliability. Oh, yes, please.
Joe, this
yes,
is Elo. Thanks for giving the opportunity. We did some study for a microgrid for Duke Energy, and the criteria they gave us is if you have one outage, you consider that reliability into reliability index. And when they ask us to do a resiliency study, they gave us the task. Could you consider multiple outage, like 2 outage? And they wanted to push that into resiliency. Doesn't go to national news, but it still belongs to resiliency because it's not the routine screening. It's more than it's not N-1 anymore. Yeah. So my question would be, would that still be okay to consider to be part of the resiliency index?
So what I guess I'm trying to describe in the prior 2 slides is that, resilience is not different from reliability fundamentally in terms of we're talking about not having electric service, at least from the utility planning perspective.
Yeah.
And so what is the threshold for calling something resilient? I think it's the conversation that the regulator and its utility and the people that the utilities are serving and the parties that are affected agree are relevant. And if you want to call certain events more than 2 outages per year resilience, that's fine with me. I mean, I'm somewhat agnostic to calling out resilience as something categorically different. I've illustrated some dimensions in which it's different, very, very different, and much more hard to make decisions around. But this example of reducing somebody's frequency of interruptions from 2 to 1, I think it's a little bit of a stretch. The CME incidents that I've been concerned about that often get reported in utility reports are CMEs of 5 or more. The same customer experiencing 5 to 8 interruptions in a year because their circuit is in some particular location or it's not been maintained and things of that nature.
Joe, sorry, I didn't make that clear. 2 interruptions simultaneously, not how many interruptions sequentially. Yeah, 2 simultaneous interruptions at 2 different locations in a small area.
Well,
so,
I guess maybe we should probably take this one offline.
Yeah.
So, Joe, it's a very important one. I think I just want to add, and I'm going to share in the chat that the report that MIT Lincoln Lab did for Puerto Rico. If you see it in the bulk power system, it's exactly what Hilo is saying. NERC binds utilities at the bulk power system level N-1, maybe N-2, but not N-K, where K is much bigger than 2. And so if you just think about bulk power system, you're not at the distribution level yet. We differentiated in that report that utility at the bulk level has to be ready for N-2, N-1 and N-2 because those are NERC reliability criteria. But NERC does not have any reliability criteria for bulk power system for K bigger than 2. And so we did a study which is proprietary for ISO New England, for example. If you have a widespread K bigger than 2 on the bulk power system, this is what I work on, and that's why I want to point it out. There is no power flow that is going to run N minus K, no linear power flow. There is no ACOPF that is going to run for N minus K, where K is bigger than 2. So I think in terms of, I see maybe Bernie will want to say something, but actually the need for software development so that you manage in resilient way when you have N minus K bigger than 2, just at the bulk level, like it happened in Puerto Rico. That's the example we were using at Lincoln Lab. Then you are going to have, it's completely outside of NERC standards. So another division, and I think Yilo is saying the same thing, N minus 1, N minus 2, you are somehow bound at bulk level to plan to do whatever, but nobody is bound to run software or to plan anything for K large. And so that is another division between the two. And we have adopted the same one, Yilo. And I think, Bernie, you want to mention something? I see you nodding your head.
No, I think these are all consistent, though. I mean, if we're worried about N minus K, we're worried about having these large events that people are going to make the front page of the newspaper. So,
yeah, but the big point is in terms of R&D and grid modernization, and that's where I have my own startup. I've spent a lot of time on this, convincing people that you need decision tools when some large events happen, like you have in Puerto Rico. At the bulk level, well, that's where everything failed. That is not covered by NERC.
But it's still one of these. Anyway,
I think it's important to recognize that what the NERC standards represent are mandatory minimum standards of planning that are required of all entities that operate both in the bulk electric system. And reliability is an overlay on that. If you can't protect against N-1, N-2, you're unreliable and in violation of these NERC rules. If you do protect against N-1, N-2, and you experience N-3, you're unreliable, but it is, in some sense, recognize that you're unreliable because the event went beyond the design threshold you're required to be reliable to. Where resilience, I think, comes in is when K gets to be quite large. But there's many events on the bulk system that I look at in the performance analysis subcommittee, where it's N-5, N-8. These are not catastrophic, situations. These are not, no one would call these resilience events. They were just very bad days. They were bad reliability days. And the system was not planned to withstand them. And the question that we're trying to answer here is, how much resilience are we going to pay for to be protected against?
Okay, and this is important to some of us. It is important to some of us because when you do planning, and you're going now into section on planning, when you do planning, people don't take into consideration how you operate the system. Depending on how you operate, how you make the decisions for reserve, for contingency, then you need more or less. This is just the only point I want to say, and maybe we can discuss it later. Okay.
All right. Well, I agree, and I know I worked with Bernie. Being able to solve these N- large K problems is a very, very important research challenge that's necessary to be able to inform the kind of decision making we want to make about whether we want to actually try to protect ourselves against these things. This is not at all to say that the research on being able to analyze these things is not important. What I want to talk about is sort of, once you know what it is you're up against, what should you do about it? And that's where this value-based reliability planning comes into play. And let me try to introduce that. I have a few slides just to introduce the concept, and I think go very straightforward. This concept was really put in place by folks at the World Bank. And at that time, this was in the late 70s, early 80s, they were financing greenfield power systems for developing nations. And they were, the charge was put to them, well, how much money do we spend on reliability? How reliably do we make these systems in these countries that don't have, power? And so this is the genesis of this method I'm going to walk you through. What they did is they looked at one, reliability, going from left to right, more reliable to less reliable on the x-axis, and cost of these systems, going from lowest cost at the bottom of the y-axis to higher cost. And what they observed from systems that they were installing, something that I think we all know as engineers, that perfect reliability is perfectly unaffordable because it would cost an infinite amount of money. And so you see that as you get to higher and higher level of reliability, going to the left on this red curve, the system costs, the costs begin to skyrocket as you try to get things more and more reliable, just because it's an important engineering problem, but it's one that can become astronomically expensive, and so no one can afford that. And so they're asking this question of how much do we spend? How far to the left can we afford to build these systems? Okay. And what they said is, you should look at the total societal cost of building these systems and what unreliability costs customers. And so they looked at this line here, this blue line, about something that we also know intuitively. The less reliable a power system is, the more it's going to cost the customers due to not having that power, and so customers will experience no interruption costs if the system is perfectly reliable. And they found it was almost a linear trend. And I'm not saying the trend has to be linear, but the concept of there being essentially a increasing cost to customers as power systems become more unreliable. That's really the point that I want to hone in on. And so what they said, we should minimize the total cost to society. So you add the blue and the red together and you get this green curve. And you look for the cost minimizing point, where you minimize the cost to society of either investing on the reliability of the power system on the one hand, and two, the remaining costs that are imposed on customers due to the unreliability that you're still left with, given that you don't have a perfectly reliable system. This basic idea is the concept of reliability value-based planning, and it's what I want to talk about in the next few slides. I think I have an example I want to talk about. So let's talk about how you get this blue line. So utilities have done lots of value of loss load surveys where they ask customers hypothetical questions about what power interruptions cost their business or how inconvenienced they might be if they're a residential customer. And you get these kinds of results. You get results that differ to the first approximation by the type of customer. Residential customers being, very low economic costs, a lot of inconvenience, of course, but from an economic perspective, it's mostly annoyance. And then, of course, larger firms with larger amounts of economic activity experience larger interruption costs. These costs can be scaled according to a number of different explanatory factors, one of the most important one being the duration. Longer you're without power, the more it costs your firm or business, the more annoyed you get as a customer. It's also dimensioned by, what time of day and even what time of year. You can imagine a hot summer afternoon being a particularly bad time to have a power interruption. Or a very cold winter night being a particular. And so there are factors that explain these differences in these costs. And I'll talk about some methods we have for trying to assess these things. So we built this tool called the ICE calculator at my lab. And it's a publicly available tool. And what we did is, what we've done is we've combined a lot of the extant utility value of loss load surveys and run econometric equations on them by customer class. Estimate what are called customer damage functions, which relate the cost that these customers of different customer classes experience as a function of things like time of day, duration of the interruption, sometimes factors about the firms. And so this tool is being used by utilities around the country to do reliability value-based planning. They would look at a circuit or a set of circuits, and they would look at the kinds of reliability improvements they might countenance for that circuit. They'd look at the change in reliability they expect from, say, putting in a distribution automation scheme in terms, which basically converts all the SAIDIs into MAFIs. And they estimate the differences in the costs that the customers would no longer bear because their reliability has been improved. And they will attribute that as a value of them making that distribution investment. They'll compare that to the cost of the distribution investment in sort of a benefit cost analysis. This is used both to prioritize circuits, internally when they're looking at which ones they might improve. And it's also used in regulatory filings when they say, this is why we want to spend $1 billion on our distribution system, because it's going to save our customers $2 billion in avoided power interruption costs that they would otherwise experience. Now, I want to say at the onset that if we used economics as the sole basis for doing reliability planning, the obvious solution is to make sure that the large C&I class has great reliability and residential customers have terrible reliability, because that's what so this is just one factor, but it's a very important factor because, we're talking about spending a lot of money on reliability. And so again, this is not the sole, we're not going to cost minimize to society because residential customers would be very disadvantaged by that. But it is an important consideration, and it's one that is increasingly being taken into account by utilities around the country and using things like the ICE calculator. But let me just say, so the ICE calculator.
Were those numbers per customer?
These are per customer numbers, and these are averages that come out of the analysis that we did with the ICE calculator.
Okay, so the residential ones add up if you look at the number of customers, right?
Well, they're not intended to be additive. They're for different distinct events. So if you have a 8-hour interruption in the morning, you're going to get one value. And if you have a 1-hour interruption in the afternoon, you're going to get a different value. So these
Sure.
refer to the cost of individual events of different characteristics.
Okay.
So the way the ICE calculator was put together is, we contacted the utilities that had conducted these surveys and got them to release the survey data to us. And so we pooled them. We had about 100,000 results ultimately. These surveys are connected over many years by a number of different utilities. And that's how we estimate these customer damage functions, which are basically econometric, regression equations. And that's what goes into the ICE calculator. But let me talk about some of the problems here. And so this is how you use it. This is a great example. This is the Electric Power Board of Chattanooga. They put in 1,200 of these automated switches. These are interrupters that are made by S&C. And they were able to reduce their SAIDI and safety in half over the 5 years it took them to install this. And so
Joe,
the
can
right
I
hand
interrupt for a
upper
second?
right. Yeah, sure.
Yeah, the beyond 8 hours, do you extrapolate those costs, or what do you do beyond 8-hour interruptions?
I'll talk about beyond 8 hours because that's really kind of the cutting edge of our research right now. That's going to be the conclusion of the talk.
And are your numbers trying to project the cost futures like car charging, and somebody in a residential who's charging their car now can't make it to work or needs to hire Uber transportation or something because now their vehicle doesn't work, or how do you time phase it so that it picks up the cost going forward?
I'll speak to all of those issues in a couple of slides. Right now, let me just explain the concept here. So in the upper right-hand corner, here's the cost-benefit analysis that Oak Ridge did of their investment, of Electric Power Board's investment. And they looked at the annualized investment cost being $5 million, but the benefits in terms of avoided customer interruption costs being $27 million. So it's highly cost beneficial from the standpoint of customers having their reliability improved. And let me just say, these SAIDI and safety numbers are just improvements in SAIDI and safety without major events. Okay. So during the course of these 5 years, they also had, and we all know, this is sort of in the tornado alley region. So in one tornado alone, in the lower right-hand corner, they did a retrospective analysis of how fast they were able to restore service to customers. And they estimate from that one event, they were able to save their customers $23 million in avoided interruption costs. And this really dramatizes the significance in terms of customer impacts of these resilience events compared to these blue sky reliability events. And it's kind of a sobering recognition that the entire year of traditional reliability benefits could be recouped in one event if it's a severe resilience event, and kind of dramatizes why the stakes are so high.
Just a clarification
Yes.
question. What are these automated circuit switches and sensors doing?
This is an incredible system. If you ever have a chance to go to Chattanooga, I know the general manager is very happy to show you they have a control center which can automatically reroute power around downed lines.
Okay, got it. So it's not like normally open switches, normally closed switches, open and closed.
Yeah, it's this incredible. They have so it's more or less a network because it's in a city, and so they're able to reroute power almost automatically upon detecting a fault.
So it is not what my husband wants to see, that when the tree touches my the wire close to my house, that it closes and recloses automatically. It's not just that, right? It's coordinated by the control center.
Exactly. And so they also know exactly where to send the crew. So not only can they minimize the total number of outage customers pretty quickly so that most customers would only experience a momentary, those that are still experiencing the sustained interruption have their service restored much more quickly because they know exactly what section of the distribution system the line is down on. And it's an incredible operation, what they have. It just really speaks to what you can do with automation.
So this is really long overdue, but why nobody else but Chattanooga does it?
Well, they have investment money from DOE to implement and pay for the interrupters. But
that's subsidy. That's subsidy, right?
Half of the cost was paid for by DOE through the ARA grants that were issued under the first Obama administration.
Okay.
But in addition, this is a very tech-savvy community that has a lot of very high bandwidth fiber optics to every residence. They in fact make more money as a city selling internet services to their customers than it really pays for the entire municipal operations.
Okay, thank you.
It's a very involved story, but this is a very technology savvy community, and maybe we can talk about them a little bit separately. But let me just talk, and this speaks to the gentleman's question. The surveys that went into the ICE calculator, some of them are 25 years old, and I don't mean to put a point on this, but these surveys were conducted when nobody worked at home. These surveys were before people had cell phones in some cases, before they had laptops with remote power supplies on them, and so they were also only conducted in certain parts of the country. So the ICE calculator can't be truly said to be statistically representative of the U.S. as a whole. And importantly, look at this last column, very few of these surveys ask questions about interruptions of long duration. And so viewing this, we've been approached by Edison Electric Institute and encouraged by the Department of Energy to launch basically a public-private initiative to have utilities pay us to conduct new surveys using a modern survey instrument to refresh the data that are in the ICE calculator. That survey will have questions that speak directly to things like how did the COVID experience affect how you operate and the losses you might experience when the power is interrupted. They likely will talk about electrification, electric vehicles in particular. They're going to ask a lot of questions in particular about not so much what is it worth to you or what does it cost you if you were without power, but like what is your resilience posture? Do you have a backup generator? How much fuel how long can you run off grid? What portion of your business can be run off grid? What is your inventory management policy? And so we're going to be able to use that information to refresh the ICE calculator in the next couple of years. So this is just an outline. Basically, we are entering into contracts with utilities across the country to conduct new surveys of their customer populations using a consistent survey form that we're going to be revising based on a handbook that we prepared for DOE a couple of years ago with modern survey techniques. There's a lot of the residential stuff is kind of a measure of annoyance. They use what are called willingness to pay or willingness to accept type surveys. Well, the state of the practice for how you ask those questions has really gone up since those techniques were first introduced. And so we've incorporated some of those ways of asking those questions into the way that we'll be conducting these surveys. But let me just describe now to the gentleman's question, survey approaches, we've been doing a lot of work thinking about these widespread long duration power interruptions because we're concerned about how do you estimate the economic costs associated with, quote, resilience events. And survey-based approaches are not well suited, because, for example, if you've never experienced a multi-day interruption, it's very difficult to postulate what it might be the impact. You have to make a lot of assumptions about, well, is it just my neighborhood, or is it the entire city? Is it the entire state? And particularly with resilience events, can I drive my car? Can I actually leave town to go somewhere else where I stay in a hotel? So there's a lot of sort of scenario issues that need to be framed to use surveys to get customers to give you a meaningful response. And very importantly, we know that these resilience events have corollary impacts on firms and customers whose power is not interrupted, but because they depend on the goods and services that they either ship to or receive from customers whose power might have been interrupted. These indirect costs, customers could never tell you what the impact of their inability to have power is on some other customer whose product depends on what they ship to them. So there is a class of tools that are available to do this. They're called regional economic models. And these the earliest versions of them were kind of the Leontief input-output, but the sophistication has gone well beyond that. And now the state of the art are these what I call these computable general equilibrium models and computable partial equilibrium models. They're pretty well established in the academic literature, but that's probably the only place where you see work published on this stuff. They require enormous amounts of data, and they're fiendishly difficult to calibrate. And so we are now undertaking an approach which seeks to marry these two approaches. So what we are doing is, we are, in fact, we're actually implementing this right now. You use surveys not so much to estimate the cost of the power interruptions themselves, but to understand how well positioned customers are to withstand or adapt to long duration power interruptions. And then you use these kinds of survey results to calibrate these computable general equilibrium models, which actually look at how sectors of the economy interact with one another when subject to these perturbations in the economic inputs, in particular the input of electricity. And so we think from clever use of surveys and clever use of these models, we can begin to estimate some of these impacts. And we actually have a study right now with the Commonwealth Edison Company, serves the Chicago area, to demonstrate this approach. We're very excited. We're in the midst of the data collection process right now. We hope to be running these models in the summer and then generating some. The Commonwealth Edison is very interested in resilience planning. They've undertaken a lot of smart grid investments. They have, many of you heard of the Brownsville microgrid. It was specifically designed to provide resilience benefits to the community of Bronzeville, specifically the police station, among other critical civic services that you want to have operating during long duration power interruption. And anyway, we're very excited about this. I can't say too much about what we found because we're sort of still collecting the data and getting these models tuned up, but we think this is a very promising approach to trying to get at this question of the widespread long duration power interruptions.
In a certain sense, doesn't this method sort of favor a hierarchical approach to resiliency as opposed to a select bottom up? So if I'm a resident, or let's take a commercial firm that is a warehouse, might have one end of the spectrum of interruption cost. But if I'm a semiconductor foundry, or if I operate clean rooms, a single 2-hour outage might cost me 2 weeks or a week of production because all my clean rooms have to be normalized and so on and so forth. So there's a big range within those categories. And wouldn't it be the case that if you mitigate some of those higher end of the spectrum interruption cost factors with microgrids, for example, or any backup really, but let's take microgrids because that's the most popular approach because of sustainability and so on. Wouldn't that change those averages and so on? So will your method be able to establish the full range and then maybe disaggregate use cases down to a way that we can understand what the mitigation costs of interruption might be in a bottoms-up approach?
Well, the objective, of course, is to sort of match the two. You know, the CGE approach is a very much a top-down approach. But, you know, and you know, to your question of the specific firms, it goes to the sort of segmentation and the granularity of the representation that's in these models. And I think we're up to about 50 sectors that we're trying to model. You know, they're not individual firms, they're groups of firms. But, you know, as you can see in this chart, you know, one of the adaptive strategies that we're asking folks about is whether they have backup generation and how that's going to affect their costs. Key issue there being what portion of your productive capacity is covered by the backup, can you support with the backup generation, and how long can you support it? And that, you know, interacts with, of course, the duration and extent of the interruption scenario. But, you know, the hope is to sort of begin to
Brian, that we follow up with this, because Joe, I think you should really meet Brian. He's working on California Energy Commission and Vanguard's things on microgrid.
Great.
Yeah. So
we have briefed the group at
later.
Thank you very much. That's great.
Yeah.
I have one more slide, and then I see there's some questions in chat. I just want to emphasize that, you know, again, economics is very important. You know, we're talking about economic decisions, you know, to spend a lot of money on resilience. And we're focused on a very specific aspect of that, those associated with, you know, the utility and the customers being without power. But there's lots of other costs that need to be considered here. And so I don't want to pretend that just having a better estimate of the cost to customers bear from widespread long duration power interruptions is, you know, all that you need to go into the resilience planning. And this is just a chart that my colleague Sunny Bayek put together, trying to illustrate the many dimensions of costs of natural hazards that go beyond what the utility is responsible for, you know, that we as a society need to think about in an integrated way, I believe, to be efficient in thinking about resilience planning. And so what I've tried to do is just try to illustrate some of the techniques we're looking at for one portion of this larger pie of considerations that need to be taken into account in resilience planning. I think that is all that I have prepared. And we have lots of publications that you're all welcome to download. They're all publicly available. And of course, you're welcome to follow up with me with any questions you have.
Thank you very much, Joe. Maybe we should start with Ning Lu's question. Ning, are you still there?
Yeah, I am here. Thank you for the presentation. I learned a lot from the policy and the view from a different world. I'm more technical. So my question is more like this. For the Chattanooga case, I think you analyzed the result. Have you distinguished that result to see how much benefit are coming from segmenting these long feeders into different smaller segments, so that when the fault happens, you basically can isolate the fault to a smaller segment. And then by doing so, you reduce the number being affected and then reduce the fault duration. Or how much is actually due to that you can actually put the feeder itself to another feeder, because that's feeder reconfiguration. I think those are two separate type of approach. And then I think the reconfiguration probably is more realistic for other areas to implement that, because you just cannot segment the feeder into so many small parts, which is highly costly and may not even be necessary in most cases. So how can you comment on that, how you analyze the results, but by more detail?
My understanding is that EPB is employing a little bit of both of these strategies. It was a very holistic approach they took. Our study was not, or actually that study that I showed results from was conducted by Oak Ridge National Laboratory using the ICE calculator. But the point was not, and these techniques could be used to inform the design choices of the distribution investments that are being considered. In this instance, those decisions had already been made. And so this was a retrospective evaluation of the investment that had taken place, not an evaluation of what alternative designs might have led to in terms of greater or lower cost effectiveness, so to speak.
So your analysis is due to the actual data sets collected in that area, but you excluded the major event day, right? If there's a hurricane comes and then which is probably beyond your control, will you consider that in this improvement, or you just more or less select the 2 years and then exclude these extreme events and then just compare them that way?
Well, I don't know to what extent any of this was taken into account in the decision to make the investment. But in retrospect, they did experience a tornado, and I did present results from their analysis of that tornado restoration effort, which showed that there was enormous savings just from that single day of accelerated both hardening in terms of the number of customers that were experiencing interruptions, and accelerated restoration of those that did experience interruptions, and that it was equal in magnitude to the annual benefit from the improvements in blue sky reliability.
Okay,
but again, this was not a design study.
Joe, it's almost
noon. Oh yes, I need to jump to another call. Actually,
no. Can we just get Professor Pedro Carvalho from Portugal?
Sure.
Pedro, can you ask your comment question? Yeah.
Thank you, Joe, for the nice presentation. I was just wondering. So you have proposed a method to evaluate the interruption costs, right? Interruption costs is just one part of the problem, because we need to understand how the events map into interruptions, right? So a grid is exposed to
absolutely, yeah. No, and right? That's why I started out with my discussion of reliability versus resilience. The challenge with resilience is the frequency and the severity of these resilience events is very difficult to predict. And yet we need to put these uncertain quantities into this quote benefit cost framework, which requires that we have some sense of how often it's going to happen and how severe it's going to be. Otherwise, we can't predict the economic impact.
But to evaluate the reliability or the resilience of a given network, you have to map a certain expected event into the probabilities of failure. And one thing is having one failure in a given region. Another thing is having many failures that are somehow correlated with each other, right?
No, I think it's a very difficult problem.
And I think there's a big challenge around that as well.
Yeah. Okay. So I think, yeah. I think we should probably, Joe, you said you have to go to another call, right?
Yes, I do. And I'll send you my slides, Maria. And I'll be happy to follow up by email with anyone who'd like to send me a
Yeah,
follow-up
so
question.
please, guys, send me questions, or you'll have Joe's email. I'm going to try to invite a couple of people next semester. There will be continuation. There are people who have done a little bit of that work, Pedro, that you're mentioning. To be continued. Thank you so much, and happy holidays.
All righty. Nice talking with everybody. Happy holidays.
Thank you.